One of the things about tension that I want you to keep in mind is, unlike many of the other formulas or forces, forces that we've dealt with, tension doesn't have a formula associated with it. For that matter, normal force doesn't either, that we just talked about in the previous video. But like the force of gravity, we have a formula for that. We have weight equals mg if you're on Earth, or in a more general sense, of course, force of gravity is capital G, the mass, two masses times each other divided by the distance between them squared. Friction has a formula which we'll get to later on. So there are, no need to go through all of them, but there are some forces have formulas. Tension does not have a formula per se. Tension is usually found by taking into consideration all of the forces on the object, and sometimes it's just an unknown and you have to find it, or sometimes it's given. What I want to point out about tension is this, some things that are interesting about it. First of all, Newton's third law says if you have an object, let's get an object here. So if you have some object that you are pulling on with some force, if you're pulling on it via a rope, this is more of a picture than a free body diagram, then, or a string or a cable or something like that, that force is called a tension force. So it is good form to refer to any force by any kind of a cable, rope, chain, bungee cord, something like that, although bungee cord may be more like a spring, to be honest with you, as a tension force. And that force, this is key, because of Newton's third law, that is the force in either direction at any point in there. So the tension has to be, that makes sense. So the tension that force has to be the same anywhere in there. I mean, tension can be thought of as how tautly pulled the string is. Well, if you pull on this string, you wouldn't expect this end to be loose suddenly, but tight here. That's like not possible. So it's going to be the same tension throughout. And the tension pulling on the block, boom, which is probably what we're considering, is also going to be the tension pulling on you. Think about it. If you had, if the block was on some sort of wheels, and this is going to be you. There's your arms, there's your legs. We're also on roller skates. When you pulled, you would both accelerate towards each other. Maybe at different accelerations if your masses were different, but you both of you would be experiencing a force, even if it was only you that, quote, you that pulled, because Newton's third law says equal and opposite. So those are the same sized tension forces, even though they're in opposite directions. But here's the interesting thing. So a common physics question that will almost certainly show up somewhere is the following. If I take, let's say I have a table, a couple pulleys, boom, boom, string between them, and then off of this string I hang some mass m, and I hang identical mass m here. What's the tension in the string? What's the tension force everywhere in the string? Now, you might say, all right, well, this is mg, this is mg, and the most common wrong answer, I cannot stress this enough, what I'm about to say is incorrect. Okay, so don't take, just because it's the first thing I say, doesn't mean it's the best thing I say. What I'm about to say is incorrect, and that is, people will tell you that the tension in here is, since there's two weights hanging off it, tension is equal to double the weight. It's actually not true. It's really only equal to mg, to one of the weights. Why, you ask? Because, think of this way. It doesn't have eyes, it can't see anything, but it can't even see on the other side to see what's holding it. As far as it knows, you've just built a wall here and tied it off. Either way, it would just be dangling there the same way. It has no idea. If I drew a situation a moment ago that had a little wall here or something, or some kind of bracket, and boom, and then the pulley, and then the mass over there, and I say, what's the tension? If this is the weight is mg, you'd say, well, if it's in equilibrium, yeah, tension's got to be mg. No big deal. It's only one weight. You wouldn't say 2 mg. But the interesting part is as far as this mass is concerned, this situation and this one are the same. Something is keeping it from accelerating to the ground. It's keeping it in equilibrium. So, be careful about that. In a tug of war, if everybody's in equilibrium, it's the force on the tension force on the string is as hard as either team is pulling. And if it's in equilibrium, they have to be pulling the same. And by the way, remember, equilibrium doesn't have to mean that they're stationary. If they're already started there was a net force for a split second, and both teams started moving, say, to the right. If they kept moving at constant velocity, you're in equilibrium. The left team's pulling just as hard as the right, but they're just going to keep moving because of Newton's first law. Yeah, that's right. So all you got to do is get the other team started, and then even if they balance you out, since you're already moving, but the tension would be equal to either pick one of their forces. Their combined force, that would be the tension, only one of them. Another thing that comes up in some of the concept questions. So there's some problems that look like this. We'll go a floor and a block and another block. Let's go another block. All 3 blocks have the same mass. Keep it simple. Boom. And there is a tension force pulling on that one. We'll call it T1. There is a tension force between these two. That rope is certainly not going to be loose unless friction is so large. I think we're going to go no friction, T2. And there's a tension force here, T3. And I don't want you to think for 1 second that it has anything to do with the length of these strings. So just because I drew this as a shorter string than this, don't think for a second that the length of the string makes any difference. Okay. So let's say we're accelerating these blocks to the left. So we're a typical situation, we say it's at rest and we start like a toy train, we start pulling on it with this tension over here. And the blocks all, since they're connected, all experience this acceleration. So all the blocks. Now, it's an interesting situation. In fact, let me clone it. Let me take all of this and clone it. Because we're going to come back to it. What the heck? Oh, darn it, that didn't work. Hold on. Boom. I'll do this first. Clone it. There you go. So we got 3 of them. So the first situation I want to look at, I'll do it in blue, is all of them as one big object. So in other words, from the perspective of this tension, that tension is, if there's no friction, the net force on the entire group of them is that tension. There is no friction, there's no other force that matters. There is weight and normal force for the whole group, but they cancel out because we're on a horizontal surface and we're not accelerating up or down, so I'm not worried about that. We're accelerating left and right. So the net force is tension 1. That means net force, of course, is equal to ma. What is the total mass being accelerated from tension 1's perspective? How much mass is it hauling behind it? Count them. 1, 2, 3m. So it's got 3m times a is equal to the net force, or tension 1. 3m. There we go. Okay, so it's hauling all 3 masses. It's got this acceleration that we already said is a number. Pick a number if you'd like. And that would represent how hard it would have to pull. Well, now let's consider, just keep that in mind.